Okay. So our next speaker is Karmel, and she's an assistant professor at University of Southern California. And she will be talking about equity promoting for medical resident rotation scheduling. Thanks again for coming.
Yeah, thank you so much. Thanks for those who are coming evening time and those who woke up today in the morning time like me for this talk. So by the way, I speak so fast, so there's an opportunity to ask me later. So this talk is a joint work with, actually led by my brilliant PhD student, Shuten Lee. It has been accepted in healthcare management science recently. And thanks a lot for Dr. Beth Hashman, who is actually a surgeon who actually motivated for all of this work. In terms of where this work lies in my big research program, I'm actually a person who does optimization under uncertainty, but this work necessitates me to stop and pause and do a little bit more deterministic approach. So it lies on my love for mixed integer programming and two of my application area, healthcare operation research and fairness promoting optimization. Like I start any of my lectures when I teach, I start with the quote of the day, and this is one of the most inspiring quotes that always inspire me when I deal with integer programming problems specifically, because they always hit you back in your face to try to solve them. In terms of the outline for today, here is it. You will forget it, so I'm just gonna skip and go directly to the problem. So for those of you who don't know, medical residents are actually doctors. They just graduated from medical school. They join a certified residency program to get specialty, to fulfill the specialty board requirements. Most programs in the US last between 3 to 5 years, and I'm going to call them PGYs, postgraduate years, which is common name here. During each of these years, they rotate through different department and service to gain the required clinical training. And most medical schools, they administer their residency program with some affiliated hospitals within the same system. Here in the US, the so-called Accreditation Council for Graduate Medical Education, ACGME, they set the guidelines and all the rules and the expectation for residency programs to actually be legitimate and stays in the game. So I'm going to go directly to define the problem, then we can go into details and all the background. The resident to rotation assignment problem consists of sets of residents, set of resident classes by E, different type of department. D is the set of all departments. Some of them are busy, some of them mandatory that the residents needs to go in. Impossibles, I'll define all of this later. Set of blocks where they are time period, and set of weeks, program rules and requirements, some staffing needs, and so on. Given all of these sets, we want to find a feasible rotation schedule, specifying resident assignments to rotation and then to vacation time. How they do it in practice, they divide the academic year to 52 to 53, which consists of 52 to 53 weeks, at least at the collaborating health system, to time blocks. Each of these blocks will consist of several consecutive weeks. Then they assign residents to block or equivalently a rotation period in a specific department, and then they decide resident vacation week. So this is kind of like a sequential approach. In order to see what I mean by a rotation schedule, this is just an example. I know it's big and a lot to digest, but let us focus on the first one thing. So here we have 5 classes, and in each class there has 2 residents. As you can see, the structure of the blocks, meaning that the length of them different between classes. And in terms of what the rotation schedule, you see this resident is assigned to the so-called night shift, then this shift, this department, and then this department. And in week 1 of their second rotation, they are on vacation. So this is how actually the rotation schedule will look like. Okay, so this is one of the oldest and most challenging IP problems known in the literature. I'm not going to go through literature review, but people know that this is a challenging problem. Why? Because it involves many residents in hospital departments, and these departments have different function. It requires you to balance a lot of class-specific educational requirements, managerial role, personal appeals, conflicting vacation requests, and so on. Now, the schedule that you construct, it must comply with accreditation standard, like the ACGME standards. It also must satisfy a lot of staffing needs, which differ between service and department. It should also respect the vacational preferences of the resident, and it should ensure equity in satisfying those vacation preferences. And if you look at many of the survey, for example, this is one of them, you will see that mathematical formulation of this problem are also extremely challenging. So people resort sometimes to heuristic approach or some decomposition technique to solve the problem. Now, drawback of the manual methods where that are being implemented in practice, they definitely generate an equitable rotation schedule, meaning that some residents will get their preferred vacation week satisfied and some don't. They are difficult to adjust once the academic year begins because, again, this is a complex problem and they do it in pencil and paper and sometimes with Excel. So in order to do that process, which takes them several weeks, again, they don't do it. And unfortunately, a lot of programs actually are dealing with the challenge of their rotation schedule do not comply with the ACGME regulation, so they are at the risk of losing their accreditation. So what to do? Of course, we call all of the integer programming techniques in order to deal with this challenging problem. I'm going to summarize the contribution and we're going to go over them one by one. We formulate this problem, we developed a new integer programming approach, feasibility problem, equity neutral, meaning that you don't consider equity, and equity promoting model. The equity promoting model necessitates developing a technique to get all the Pareto optimal solution, which is a new algorithm, the Pareto Search Algorithm. In order to implement this in practice, we worked with our collaborator to develop a user-friendly tool so they don't see the crazy math. You will later see that they just click, and they get the rotation schedule. And I will present some practical insights that show the potential of our approach in enhancing fairness in practical environments. Okay, let us first start with the IP formulation. How we can turn this messy optimization problem into some art. And why I'm saying art? Because this problem is challenging to model and solve. So what we did, we came up with a new formulation. The key decisions of this formulation is the first one says simply if a resident is assigned to a department in a particular block. The second one acts here if a resident works in a department in a specific week. And the last one just says if a resident in a vacation in week W in a particular department. I'm not going to go into the formulation in details, but before I present it, the key innovation here is what allowed us to solve this problem is we define many sets that are related to the problem that allow us to reduce the size of the formulation. Some of them will appear in the constraint. So again, this is a feasibility problem as it's defined in the literature, as defined in the practice, so there is no objective. The first constraint just says each resident is assigned to at most one department in each block, and this is a part of the sets that I talk about. So we define classes of residents. There is a set of residents in each class and the blocks that are specific for this class. Each resident must be assigned to required department exactly once. And this is the set of the required departments defined either by ACGME or by the residency program. Residents that are not assigned to rotation in impossible departments. So this kind of reduces the search space for this variable because there are some impossible departments that some residents cannot rotate in. And residents cannot be assigned, I think I repeated this mistakenly, but this should be de-required and this should be impossible blocks. Other constraints that are essential, each resident by the ACGME should, for example, get 4 weeks of vacation during the academic year. So, for example, this constraint allows you to set that requirement. Of course, the length of the rotation period must satisfy the minimum and maximum rotation length. So this is satisfied by this constraint. There is some staffing requirements. So each department says I have a minimum and maximum number of residents of each class. So this constraints ensure these limits. And there are some the so-called busy departments. Without going into detail, these departments requires residents to show up every single day, every single week when a resident assigned to rotate. So this prevents them from taking vacation. So they are not by the design of these departments, they cannot take vacations. So these constraints prevent that from happening. You need to limit the number of residents on vacation in each block. Otherwise, the optimals or the solutions here will be like all residents on vacation. Each resident can take at most this number of weeks of vacation in each block, which is ensured by this constraint. And this constraint, the last one, simply says if you are assigned into a department in a given block, in each week you are either on a vacation or working. And given that this is binary and this is binary, we actually show that you can actually relax this integrality requirement in variable v. Okay, so let me just step back. So this feasibility problem just gives you a feasible rotation schedule. However, the number of satisfied vacation requests is not that large, simply because you did not have such an objective. So the equity promoting neutral approach is to say, let me maximize the number of satisfied requests. And now I am adding all the constraint here. And this is just the term that says, find me a rotation schedule that maximizes the number of satisfied requests and also comply with all of these rules. This is great. We can actually efficiently solve this using Gorobi or Simplex, using very quickly. But as you can see, since we focused on maximizing the number of satisfied requests, it leads to disparity in satisfying vacation requests. To show you what I mean by this disparity, so this is an example, simple example. This is the vacation schedule from the equity promoting neutral formulation. And in terms, so this is 5 residents. You can see this resident has 1 vacation request satisfied, but this resident and this resident, they have 2 vacation requests satisfied while the others have only 1. So this actually leads to disparity between them, why some residents have more vacation requests satisfied while others don't. So in order, of course, there is a room to prevent that. So we actually derive an equity promoting counterpart. The first objective of it remains the same as the equity neutral. We want to maximize the number of satisfied vacation requests. So this is our efficiency measure. And the second one is I want to minimize a measure of inequity. So give me the vacation schedule. I want to minimize the disparity in satisfied vacation requests. Since we still have the same constraints, so it's still satisfy all the rules and constraints set by ACGME and the residency program, and also additionally produce fair vacation schedule. But for those of you who works on this, by objective or this type of conflicting objective, these 2 objectives are conflicting. So we need a method to actually generate all these Pareto optimal solution and give them to the residency program. Which I will discuss next. But before I go, I want to a little bit give you an examples of some fairness measure. This type of fairness measure leads to a kind of like linear reformulation. They call deviation measures or mostly deviation measures. Some of you who works on this space, they know them. I would forget about the math, but I'm going to use variable y as the number of satisfied vacation requests. For example, this measure range is basically the difference between the maximum number of satisfied requests for a residence and the minimum, the one who gets the worst, which is the minimum number of satisfied vacation requests. Okay. So let us dive into how to solve this equity promoting formulation to get to this set of non-dominated point. I'm just going to say that using the epsilon constraint method, you cannot solve that formulation, and I will show computational results later. And definitely we cannot use the weighted method because it won't give us all the non-dominated Pareto optimal solution. And this is the second half of the art after solving the problem is how do you actually can solve it. I'm going to go through a little bit of notation. I'm going to call this set F as the set of feasible set of equity promoting formulation. This simply going to be the set of Pareto optimal solution, and this set P is the set of non-dominated point. First, let us consider this problem where we set the equity measure to 0 and we say, find me the vacation schedule that maximizes the first objective, which is the maximum number of satisfied vacation requests. We show that by doing so, we get one Pareto optimal solution to the problem. Second, this proposition simply say, well, let me solve the equity neutral model, which give me this optimal value. I'm going to fix the first objective. So I want the number of satisfied vacation requests to be to that value. And I'm going to find the value of the inequity measure of rotation schedule that minimize the value of the inequity measure. And we show by doing so, you actually can get another Pareto optimal solution on the curve. So why are we doing that? So these two observations actually show you that any non-dominated point associated with non-dominated solution satisfy the following. The first objective, this one, is actually lies between these two values, which are simply this one, where you fix the equity measure to 0, and this one, where you fix the number of satisfied vacation requests to V bar. And then the second objective, which is the inequity measure value, it's between 0 and this value here. So you kind of now know what's the ranges of these two objectives for each of the non-dominated point. The second observation is that the difference in the total number of satisfied requests between two non-dominated vacation schedule is at least 1. And why did we care about all of that? Because this gives us a way to search for this non-dominated vacation schedule. Basically, if you have a non-dominated vacation schedule, the subsequent one might retain the same number V, same satisfied requests in V, while fulfilling additional requests. So we use these 3 observations to develop our algorithms, but I'm going to go through one example to show you which will illustrate what I'm doing next. So here I have one resident, I have 4 residents. In this schedule, this resident got 1 vacation request satisfied, and this resident got 1 vacation request satisfied. And let us consider the Gini deviation as the equity measure. So the number of satisfied requests 2, and the measure of equity is 8. Now, suppose I can feasibly satisfy 1 additional request. If you give it to this resident, which has already 1 vacation request satisfied, then the value of increase by 1, the F1, but the equity measure increases to 14. Now, instead, if you give the additional request to one of the residents that have lowest number of vacation requests, then you actually increases F1, but also decreases F2, which is the inequity measure. So we leverage this observation to develop our algorithm. Okay, so this is in words, just to show you that by doing so, you actually get an optimal solution. So I'm going to skip that, and you can see the paper for the math. Now, the steps of this algorithm, in the step 1, we identify a Pareto optimal solution with the smallest value of the inequity measure by, again, solving this problem which you have seen in the proposition. In step 2, we find the minimum value of F1 by solving the maximum value of F1 by solving the equity neutral model. Then, using the observation that I show you in step 3, which is the most critical step, we identify all the optimal rotation schedule that has F1 between these two values. However, this step gives you all solutions, so you need to kind of extract only the non-dominated solutions. Let me see how I'm doing in good time. So I was planning to explain this step in detail, which is the key innovation, but it sounds like I have only 13 minutes, so I'm just going to skip the mathematical details and maybe go to the numerical insight, which is actually turning your math into wisdom. So in terms of test instances, they are all based on our collaborating health system data from 2018 and 2023. We varied, as you can see, instance 1, instance 2, and 3. We vary the number of blocks for each class, and we also vary the number of the required department. This is just the table show you the so-called mandatory department, meaning that departments that residents needs to rotate in. Those that are highlighted in bold, this is just busy department. And as you recall, I defined it earlier, you cannot have vacation on a busy department. We solve instances with this number of residents, and 185 is a representative instance of a large residency program, but later I will show you that we also solve hypothetical instances. The number of weeks in the academic year is 53, and we use 2 techniques to generate vacation requests. The first one is you generate preferences from non-overlapping weeks, And the second one, you just divide the academic 3 years to 3 parts, and then you start to randomly sample vacation requests from each part. And the educational requirements, staffing needs, and other practical constraints, they are actually from our collaborators. Let us first look at the computational performance. I'm going to tell you that using the epsilon constraint method, we actually were not able to solve any of the generated instances at any size. And in particular, for those inequity measures, it's actually terminated with optimality gap of at least 60%. However, using our methods, I know this is a big table, we were able to solve all the generated instances, and here the time in second. So for example, the range of solving the first instance is really between 62 and between 140 seconds, and maybe this is less than 30 minutes. And even the large instance, we can solve it in under 2 hours. And let me pause here and say, rotation scheduling, if you look at most papers, you will see that actually this problem is not solvable in any time frame. So we were happy to see that this solution time, actually the required time to generate all non-node dominated rotation schedule. And in terms of the equity neutral model, we actually can solve it fairly quickly within maybe 60 seconds, even if you give me a 500 residents to solve. So this is good. Now, in the second insights here, I'm going to show you the Pareto fronts that we got. In the x-axis, this is the number of satisfied requests, which is F1, and each of these y-axes, this is the value of the inequity measure. So a couple of insights that you can see here. You can see that in all of these figures, even let me focus on one, all the non-dominated points occurs with F1 being 108 and 193. And you can see this point has an inequity measure of 0, so all of them. And all of them reaches this most efficient solution, which is the least equitable, that maximize the number of satisfied requests. So this one is basically the solution to the equity neutral model, which show you how much using just equity neutral formulation leads to disparity, because it's maximized the value of the inequity measure. Another observation, this star here, this is the feasible schedule, which is obtained by solving the feasibility problem. And this is tell you that approach that consider the problem as a feasibility problem leads to solutions that are way inferior to any of the solution that you got using our model and our algorithm. The third observation, probably some of you has noticed, different inequity measures leads to different trade-off curves here, as you can see. And also some measures leads to different number of non-dominated points. So for example, the range produces only 3 non-dominated solution, while the mean deviation here produces a larger number, this one produces a larger number, and so on. If you ask me, does our collaborator has a preference? I will tell you no, because they have no idea what these measures mean. But definitely they recommend that they prefer something like this, because it gives them multiple rotation schedules. So if they pick this one, for example, they know that they can satisfy 135 requests, but maybe this is kind of will lead to a little bit of disparity. Good. So the next question, which is the fairness folks ask typically, is what's the impact on efficiency? And efficiency here in our problem is on maximizing the number of satisfied requests. So we use this measure, which is the price of equity, which is the loss of efficiency incurred into pursuit of fairness. Here, V bar, if you remember, this is the optimal value to the equity neutral formulation. And F1V is the value of the number of satisfied requests if you give me one of the non-dominated points on the Pareto curve. Okay, so this is the value POE, which is the price of equity. I know this is a little bit cramped, but let me break it for you. You can see that this POE is actually ranges between 0.44 and 0. This one is the most efficient, and again is associated with the equity neutral formulation because it leads to the maximum number of satisfied requests. This one is the most equitable. One of the key insights that you can see here is that, but let me first say that the points here that are marked with a specific color says the the measures that actually give you these points. One key observation is that the max mean deviation, so this measure, you can see it in all of these bars, because it's, again, it produces the largest number of the non-dominated points. Additionally, the max mean deviation, it gives you this non-dominated solution with this range of POE that none of other measures can identify. So not only generates more non-dominated solution, but also gives you some points that have a little bit lower or higher POE. Okay. The last question that one would ask, then why don't we adapt the existing models from the literature? So most of these existing models, they construct the rotation schedule, so which meaning that assign residents to blocks and department, and then they solve a different problem, also our collaborator, to construct a vacation schedule. So how much better our integrated approach that integrate both can perform compared to the sequential approach? Of course, the sequential approach depends on which feasible schedule we feed in. So in the results here, we tried a different Z-bar feasible schedule, which is here, you can see them on blue in this curve, here and here and here. And the quickest observation you can see is that the non-dominated rotation schedules that we obtain using our method, they dominate these that's being obtained using the sequential approach. So this shows you that the sequential approach actually will give you a rotation schedule with lower number of satisfied vacation requests and higher value of the inequity measure, which tells you adapting this approach has some negative consequences in practice. Okay. The last piece, we have a lot of insights in the paper too, is forget about all of this math. How can they implement it in practice? Which is actually the art of all arts. Because most of the time we develop all of these crazy mathematical techniques, but then really practitioners, they don't have optimization expert. So we develop a new tool, which is presented here. This tool has two user interface. This one, the input interface, basically what the clinician needs to do, we have created a template for them. So they click here and they download it. It fills all the input parameters needed in values for our optimization model. Here we tell them, choose the file, download it, fill it out, and then upload it. And they only need to do is to click here. Once they click here, there is some crazy math happening in the background. It solves the problems, generate all the schedules. And then in the output interface, you can download the schedule, which is the rotation schedule, and also download the vacation schedule. And that's it. They don't have to look at the math. They don't need to use algorithms, but basically they have to use just this tool, which is click, and that's it. And they get the results. They were particularly happy to see this because the shift residence is actually spending from 4 to 5 weeks and even more to create the rotation schedule by hand or by Excel. So this is, I think, the most practical contribution one could get. And by the way, if some of you are working on this problem, the tool is available online. You just need a password for it. So feel free to contact us to give you access to it. Okay, so I know I skipped a lot of the mathematical techniques, but the paper is available online in order to cover everything. I hope that what I presented show you that our approach, we developed new models for this problem, a little bit about our algorithm, a little bit about our user-friendly tool. Some of the key insights is we definitely show the computational efficiency of our approach, and I'm going to emphasize that this type of a problem is reported historically that is challenging to solve, and there is no computationally efficient technique to it. We show a new insights to the literature, the trade-off between the equity and satisfying vacation requests. We show how to approach it, and we show that adapting feasibility problems or equity neutral leads to unfair vacation schedule. And above all, by streamlining this traditionally manual and error-prone task, it has a strong potential to enhance this educational experience for residents, and most importantly also for those poor shift residents that spends hours and weeks and months trying to do all of that by hand. I speak like a train, so I'm gonna pause here and thanks everyone here and open it to questions. or however, Salva want to, deal with it.
Thank you, Karmel, for your talk. And to all of you, so we will set up the breakout rooms now so that you can, you can stop sharing the screen if you want.
Yeah, and
So that
we
you can,
look. I was just going to say we look forward to seeing everyone on the next dots, which will be on Friday, November 7th, with Thomas Rothbosch and Leo Lozano speaking. So we'll see them.